Hello everyone, let's go ahead and talk about the post-lab calculations for this experiment 2. And in this experiment, we are looking at the principles of Le Chatelier's principle. Okay, so what is the Le Chatelier's principle? Basically, it says if you attempt to change a system in chemical equilibrium, it will react in such a way as to counteract the change you attempted. Okay, so it's going to go back to a equilibrium if you try to disturb the system already in equilibrium. Okay, so let's see our first observation. Looking at methyl violet indicator in water. Okay, so you should have watched the video, and you can answer this first question without even my help. Okay, so acid base indicators color of methyl violet in water. So there is an equilibrium that exists in this methyl violet. What is the equilibrium? We can represent methyl violet indicator as HMV, and this is yellow in color in this form. Okay, and this is in equilibrium. When it forms the ionized form Mv minus, meaning hydrogen ion of the indicator has been released. So you have H plus and Mv minus. When the Mv minus an ion is formed, the color is violet. Okay, so you can see that exists between yellow and violet forms. So color of the methyl violet in water, you can watch the video and write down the color. Then you know in water which form it exists. If it is yellow in color, then HMV is the form that it exists. And if it is violet in color, that's Mv minus. Okay, but you only have to write the color of the methyl violet in water. And then you also be seeing in your video, it is there are two reagents that you are adding. One is ammonium hydroxide, another one is sodium hydroxide. Okay, and also another reagent possible, that is hydrochloric acid. So you add these three reagents, and then you're going to see which reagent is making the color change. If you start with yellow, which reagent you add to make it to violet. If you started violet, which reagent made it to go to yellow. So you write down that answer over here, which you can do by watching the video. And then reagent causing shift back. After you change it to the other color, you again add the other reagents. It could be the ammonium hydroxide, sodium hydroxide, or hydrochloric acid. And then you will see which one causing the shift back. Okay, explain by considering how changes in H plus will cause reaction 4 to shift to right and left. Why the reagents in step 2 and 3 cause a solution to change color. Note that reactions 3 and 4 must both go to equilibrium after a reagent is added. Okay. So explain by considering how changes in H plus will cause reaction. So hydrogen ions. So when you add hydrogen ions in the form of acid, right? So the acid H plus will protonate Mv minus. When you add acid, if it protonate Mv minus, then you will be getting in the acidic medium HMV form. Okay, but when you add a base, what does the base do? Base would remove a hydrogen ion in acidic medium. So our acidic component is HMV. So when you add a base, hydroxide ion, that will remove the hydrogen ion, acidic hydrogen ion from HMV. Then by adding a base, what do you think? The equilibrium will shift to the right by adding a base. Equilibrium will shift to the left by adding an acid. Okay, so the acid will produce the yellow form, and then the base should give you the violet form. Okay, so that is how the equilibrium will be shifted by changing the H plus ion concentration. Okay, and then the next one, solubility equilibrium, finding a value for Ksp. So what is the Ksp? K stands for the constant, equilibrium constant. Sp stands for solubility product, Ksp. Normally, a product will be formed as a precipitate when it reaches its Ksp value. Ksp is calculated by finding out the concentrations and then as a product of the concentrations. When the reagents or the reactants, product of the reactant concentrations, reach the Ksp value of a particular compound, then we will see that it would precipitate. Okay, now let's look at that concept with this reaction. Volume of 0.3 molar lead nitrate, 5 milliliters, and then number of moles we can find by looking at the volume we use. So this experiment we are going to make lead chloride. So you take a test tube, about, you're going to put 5 milliliters of lead nitrate, PbNO3, and we are going to make lead chloride in this solution. So you add 5 milliliters lead nitrate, and to this you're going to be adding hydrochloric acid in 1 milliliter increments, and then the molarity of the hydrochloric acid is going to be 0.3 molar hydrochloric acid. So what is going to happen when you add hydrochloric acid? You want to begin with, you have lead nitrate. All nitrates are soluble in water. It's going to be a liquid. Now you add hydrochloric acid, 1 milliliter to this one, and then you shake the test tube to mix the reagents. So what's going to happen? You have lead nitrate, PbNO3, plus you are adding hydrochloric acid. Double displacement reaction happens. So lead nitrate and hydrochloric acid, you're going to form lead chloride, PbCl2, plus HNO3, nitric acid. Okay, and if you balance this, it would be like that. And lead chloride is a solid, but the solid will start form when it reaches the Ksp value. So this is a solid. Okay, and nitric acid is a liquid, aqueous solution. So when you add your first 1 milliliter to this one, when you mix it up, you will see a precipitate forms. But then you add 1 more milliliter of hydrochloric acid, and then you will see more of the precipitate has been formed. So you can keep on adding more, and then the more will precipitate. But when you see a considerable amount of precipitate adds, then we know it had reached its Ksp value. So we can stop adding the amount of hydrochloric acid. To attain a considerable amount of lead chloride precipitate, so you will be adding 2 milliliters. Okay, volume of 0.3 molar hydrochloric acid added. So then you will see a white precipitate formed at the bottom when you add 2 milliliters. Okay, and then you can find out the number of moles of chloride added. We can do that calculation already. Now we started with 5 milliliters lead nitrate, and the molarity of lead is 0.3 molar. Okay, so then the volume is 5. So the number of moles are going to be molarity times the volume. Molarity is 0.3, volume 5 into 10 to the negative 3. So the number of moles of lead ions added, 1.5 into 10 to the negative 3. Excuse me. Similarly, you can find out the number of moles of chloride added. So the stock solution of hydrochloric acid is 0.3 molar, 0.30, okay, times the volume is 2 milliliters. So 2 into 10 to the negative 3. I'm calculating the number of moles of chloride added. So 0.3 times 2, that's going to be 0.60. Should be 2 fix over here. Okay, 2.0 and then 0.30. Okay, 0.60 into 10 to the negative 3 You know how to do this calculation. Even if I didn't write it here, you should still be able to do it. So it's going to be 0.60 into 10 to the negative 3 moles. That's the number of moles of chloride added. Okay, and then what you're going to do is we're going to look at and see what is going to happen for this precipitate when you put it in the hot water. So you should have watched your video already. So when you put it into hot water, what is happening to this precipitate that you made? Just write down your observation over here. And what happened to it? You put it in the ice bath again after you heat it up. What happened to it again when you put it in the cold water? So you can write down that observation here. After it cools down, you will see the precipitate reforms. Okay, so now your precipitate over here, to this one you're going to be adding water. So now we made lead chloride. You're going to add water in 1 milliliter increments. What are we doing by adding water? We are diluting the solution. Right? Now lead chloride is a precipitate. You add 1 milliliter, you shake it up. Another milliliter, you shake it up, and likewise you add several milliliters of water. As you keep on adding water and shaking and mixing it, you will see when you add 7 milliliters of water, lead chloride dissolves. Why lead chloride dissolve when you add water? Because now we are diluting the solution and we are making lead chloride less. Concentration of lead ions and chloride ions are going to be less in your mixture. Remember, once you make your lead chloride PbCl2 solid, this is in equilibrium with lead ions and chloride ions. So by diluting, we are lowering the concentrations of these. So what's going to happen to the equilibrium of the reaction mixture according to the Le Chatelier's principle? If you are losing or decreasing the products, which is your lead ions and chloride ions, so then the reaction should go forward. Meaning by adding water, you are diluting, so the lead chloride dissolves. Okay, so to dissolve lead chloride, we are adding 7 milliliters of water. Okay, and at that point, what is the total volume of the solution? 14 milliliters. Because you started with 5, that's lead nitrate, add 2 milliliters hydrochloric acid, 7, and you add 7 milliliters of water, so the total volume of the solution is 14 milliliters. Okay. And then it is asking, explain why lead chloride did not precipitate immediately on addition of hydrochloric acid. What condition must be met by lead ions and chloride ions if lead chloride is to form? If lead chloride PbCl2 is to form, then the concentration. So if you write the solubility product of lead chloride, how do you write the solubility product of lead chloride? That's Ksp equals lead ion concentration, and then we have 2Cl minus concentration raised to the power 2. So if the product of this value reaches the Ksp value of lead chloride, then we would see a precipitate. When you add just 1 milliliter of lead hydrochloric acid. When you add 1 milliliter of hydrochloric acid, there were not enough concentration of chloride being added to reach the Ksp. So when you add 2 milliliters, yes, now it reaches the Ksp value of lead chloride. The product of this two concentration reaches the Ksp value, so then you will see a precipitate form. So that is the explanation why lead chloride did not precipitate immediately on addition of HCl, because it doesn't have enough chloride ions, or the product of the lead ions and the chloride ions had not reached the Ksp value of the lead chloride. Okay. B. Explain your observation in step 4. In which direction did reaction 5 shift when heated? Observation in step 4. So the step 4 is observation in hot water. In which direction did reaction 5 shift? So what is the reaction 5? Reaction 5 is, okay, so the reaction 5 is the one that I just now wrote. So this is the reaction 5. This one is reaction 5. Okay, let's talk about here. Reaction 5. Explain your observation in step 4. Step 4, what we did? We heated the reaction, lead chloride, once a precipitate is been formed. What happened when you heat it? If you watch the video, when you heat, lead chloride become soluble. All the solid lead chloride, the white precipitate that you made by adding chloride, it completely dissolved the lead chloride precipitate and form lead ions and the chloride ions. What must have happened to the value of KSP in the hot solution? What does this tell you about the sign of? So the solubility increases. So the solubility had increased when you heat it up. So that's why it became soluble. What does this tell you about the sign of delta H in reaction 5? What is the sign of delta H? So when you add heat, you made more of the products. So what does that tell you? So let me write that reaction again. We have PbCl2, which is a solid, and this is our equilibrium, lead ions Pb2 plus and 2Cl minus. So you heat it. As you heat, you made more of the lead ions and the chloride ions. It went to this direction. That was visually we observed it. So what do you think this reaction is? It exothermic or endothermic? Now remember, in exothermic and endothermic reactions, we can consider heat either as a reactant or a product. If the equilibrium shift, making more of the lead ions and the chloride ions, these two products, if you made more of the products, what must have been added? Is the heat going to be a reactant or a product? When you heat it, if it dissolves, so then the heat is going to be a reactant. Heat will be in this side. Right? So when you add the heat, lead chloride dissolve to give you lead ions and the chloride ions. Why the lead chloride dissolved when water was added? No, not, we are still in B. Explain why your observation is step 4. What must have happened to the value of KSP? What does this tell you about the sign of delta H in reaction 5? So reaction 5 is lead chloride forming lead ions and the chloride ions. So the reaction 5, meaning reaction 5 is an endothermic reaction. Okay, because when you add the heat, if it produces more of the products, so heat is considered as a reactant. When you add a reactant, it gives you more of the products. According to this reaction, reaction 5 is an endothermic reaction. Reaction 5. But the formation of lead chloride is an exothermic process. The reverse, lead ions and the chloride ions together. I have written here the equilibrium constant. I should have written a positive charge between these two. lead ions Pb2 plus 2Cl minus. Okay, that's the equation 5 which I have written over here. Reaction 5. So reaction 5 is endothermic process, meaning the dissolving lead chloride, we need heat. But the reverse, the formation of the lead chloride, excuse me, lead ions and the chloride ions together, formation of the lead chloride is a reverse reaction, is exothermic. Okay. And C, explain why the lead chloride dissolved when water was added in step 5. What was the effect of the added water on lead ions and the chloride ions? In which direction would such a change drive reaction? I talked about that earlier also. What happened when you add water? So we are making the solution more diluted, right? What do you mean by dilution? The concentrations of these two, decreases. So if you decrease the concentration of your product, what's going to happen? The equilibrium will shift to the right, making more of the product. So that is the Le Chatelier's principle in work, because when you disturb a reaction by making a dilution, so then it will counteract by making more of the products. How can it make more of the products or increase the concentration? By dissolving lead chloride. Okay, so that's why when you add more water, reaction mixture become diluted, lead ions and the chloride ion concentration decreases. To counteract that change, lead chloride will start making more of the lead ions and the chloride ions, shifting the reaction towards forward reaction. It will go to the right side. Okay, and then the next one, excuse me, given the number of moles of lead ions and then the chloride ions in the final solution in the step 5. So what is the final solution in our step 5? Step 5, we add water, just enough water to dissolve lead chloride, 7 milliliters. Okay, so just to completely dissolve, meaning at that time we have reached the KSP value. We are dissolving, we are dissolving such a way that your reactants and the products are in equilibrium. Okay, so to dissolve we add lead chloride. At that time the volume of the solution is 14 milliliters. Given the number of moles of lead ions and chloride ions in the final solution in step 5, where we have 14 milliliters and the volume of that solution, calculate the lead ions and the chloride in that solution. Okay, now lead ions, we found out the number of moles of lead ions and the chloride ions. See, we calculated number of moles of lead ions in step 2, 1.5 into 10 to the negative 3 moles. And we also calculate the number of moles of chloride ions, that is 0.60 into 10 to the negative 3 molar in step 3. Now we can calculate the concentrations. You guys know how to calculate the concentrations. So the concentrations are basically number of moles over volume. Okay, so the lead ions going to be Pb2 plus, concentration, number of moles are going to be 1.5 into 10 to the negative 3 moles, and you divide by the volume, which is 14 into 10 to the negative 3 liters. That will give you lead ion concentration. You write it down over here. That would be 0.11. Similarly, you calculate the chloride ion solution. That would be number of moles of chloride ions, 0.60, and that's the number of moles. You divide by the volume, which is again 14 into 10 to the negative 3. Okay, and that will give you chloride ion concentration 0.043. just do these calculations and see if you're also getting the same values. And then you can calculate the KSP, which is going to be the product of these two concentrations. So 0.11 would be the lead ion concentration, and then the chloride we just calculated 0.043, and we need to raise this to the power 2 because there are two chloride ions, and this will give you the KSP value. You can write it down over here. Okay. And then the next one is complex ion equilibria. And for this one, we're going to be using a cobalt chloride complex with 6 water molecules. Cobalt chloride hexahydrate, which is a magenta color complex. It's the solid form that you need to write down. What is the color of copper chloride? This also tells in the video. You write down what is the color. And then the color in solution. So you put this in a test tube, maybe a pea size amount over here, and then you put hydrochloric acid into this one. Then what is the color of the solution in hydrochloric acid? Now this complex cobalt chloride, it exists in a chemical equilibria. So the equilibria is cobalt, so this is the equilibria, COCl4, cobalt chloride. Cobalt hexahydrate, 6 water molecules having charge 2 plus, and then when you add chloride, it's a ligand. Chloride, when you add, it can exchange this water molecule to give you a tetra ligand complex, cobalt chloride, COCl4, -2 charge, plus 6 water. So this is the equilibrium of the cobalt chloride, cobalt hydrate complex in water. Now, if you start with cobalt water, so this is what we started with, because that is the form that exists in the original compound. We're going to be using cobalt chloride hexahydrate. Okay, so cobalt chloride hexahydrate, so this is the form that exists in the solid form. Okay, and then you add hydrochloric acid. So you will see the color of that complex. What is the color? Cobalt water complex is pink in color. So this one is pink in color. But when it forms the cobalt chloride complex in water in a solution form, this would be blue. This is blue in color. Okay, notice a solid form, cobalt chloride is magenta in color, but when you add hydrochloric acid, it exists in this form, cobalt chloride. So that is why you see the color in solution, 12 molar hydrochloric acid. You will see, watch the video also, it would be blue in color. Okay, and this equilibrium is given in your textbook. And then what you're going to do is you add water to this solution. So this is the blue solution, and then to this one you add water. So what's going to happen when you keep on adding water and you shake it? So then equilibrium will shift to the left, because these ligands, so the chloride and water, they are called ligands. They can be exchanged. So initially we had cobalt chloride, now you add water. So the chloride will be replaced by the water molecules and it forms the pink cobalt hexahydrate complex. So the color in the dilute solution is going to be pink. And then you're going to be heating up this solution. You heat this solution and then you will see the pink color will become more darker. So the color of the hot solution, again, you can say it's a dark pink or maybe magenta or maybe purple in color. In the video, it says it's purple in color. So you can see basically it become more darker pink. And then you cool it down, color of the cooled solution. When you cool it down, what's going to happen? So the color will become again pink. Okay, you can write it down in this space. It's going to be pink. You watch the video. And then color of the cobalt 2 complex ion present in solution. Now, once you figure out the colors and you know the pink color is due to the cobalt hydrate complex, whereas the blue color is due to the cobalt chloride complex. So the next steps are very easy. You just have to figure out which complex exists and then what is its formula. Okay. So the formula of the cobalt complex is 12 molar hydrochloric acid. So in 12 molar hydrochloric acid, which compound do you think exists? In hydrochloric acid, is it going to be the cobalt hexahydrate or the cobalt tetrachloride? Which one in hydrochloric acid? It should be this complex right there. You just have to write down that name. Formula of the cobalt complex. COCl4 2- is what exists in the 12 molar hydrochloric acid solution. What about in the diluted solution? What is the color in the diluted solution? Pink in color. So then what should be the complex going to be? Then it should be cobalt hexahydrate complex. That's easy, isn't it? And then what about the hot solution? Hot solution, it became darker purple, darker pink or purple. So it didn't become blue. So meaning it's still the cobalt hexahydrate complex, which is cobalt water hexahydrate. What about in the cool solution? It's still a pink, a variation of a pink. So it's going to be the same complex. Okay, that's easy. Explain the color change that occurred when water was added to step 2. Consider how a change in chloride and water will shift reaction 7. We talk about that. What water was added in step 2. So what happened when water was added? So then which direction the equilibrium shift? Equilibrium shift to the left side, right? Because you add water. Water is a product in our equilibrium. Okay, so if I rewrite the equilibrium, it is going to be like this: cobalt water hexahydrate plus chloride ions COCl4 2- plus 6 water. So to the blue complex, you add water. Water is a product. You add this one. So then the reaction should shift to the left side because you're adding one of the products. When water added, consider how a change in chloride and water will shift reaction 7. So reaction 7, which is this reaction, it shifts to the left side. Okay. So that's the reaction 7. Yes. Okay, so the chloride ions will be replaced by the water that you added and it gave you the pink complex. Okay. And then the diluted solution was heated. So when you dilute it, when you add water, it became pink. You heat it up and then it becomes more darker. What does that mean? If it become more darker pink, which direction has it favored? It had favored formation of more of the cobalt hexahydrate complex, isn't it? So what has happened to the Kc? Kc will decrease if you increase the heat. Okay, so heat is a product in this reaction. That is why when you add the heat, reaction will shift to the left side. Okay, so heat. So what happened? The pink color predominate when you heat, meaning heat cannot be in the same side as the pink. So then the heat has to be in the blue side. Heat is a product. So when you add one of the products, what would happen to the reaction mixture? It would shift equilibrium to the left side to counteract the added heat. Okay, so that's why we saw a formation of more of the cobalt water complex and becoming more darker pink. So basically when you add heat, Kc will decrease, okay, in a exothermic reaction. So this is the forward reaction is exothermic, going from hexahydrate, cobalt hexahydrate to the cobalt chloride is an exothermic reaction. So in an exothermic reaction, if you add heat, Kc will decrease. Okay, and then how did increase the temperature if the value of the Kc decreases, because now when you add heat, Kc want to get back to its equilibrium, so it decreases. And what is a sign of the delta H for the reaction 7? So this is the reaction 7. Reaction 7 is written as this form, cobalt hexahydrate becoming cobalt chloride. So this, you should consider the reaction 7, the forward reaction, formation of the chloride, cobalt chloride. Since we find the heat as a product, so the delta H, the sign of the delta H is going to be less than 0, meaning it is negative, which is an exothermic reaction. Exothermic reaction. So in exothermic reaction, as you increase the temperature, Kc will decrease. Okay. And so we only do ABC parts. We don't have to worry about the other one, dissolving insoluble solids. I hope you understood the concept of Le Chatelier's principle, how by changing the reactants and the product will shift the equilibrium either to the left side or the right side. Also how to calculate the equilibrium constant, and also looking at a colorful ligand complex, coordination complex, and how the ligand exchange and how the temperature affect the Kc and the position of the equilibrium, either going left side or the right side. Okay, all right then, talk to you later. Bye bye.